can we explain why? We can try. As we already discussed before, when the both slits are open, there are two equiprobable opportunities for an electron to reach this detection screen and to go to this prohibited point. It can go through the upper slit and it can go through the lower slit. Since it is true randomness, we now know that it chooses both these opportunities, but in different universes. Since everything else in these universes, except the electron path, is identical, we can combine these two pictures in just one. Now, the interesting part. Apparently, the state of an electron is not a very straightforward thing. It is defined by many parameters, but we now need only one of them. The famous American physicist Richard Feynman, who was also the greatest teacher, in one of his popular books proposed to use this image of a clock. The book, by the way, is called Quantum Electrodynamics, the Strange Theory of Light and Matter. It was written for a very broad type of readers, and there's almost no math in it, just the explanations. Great book. If you have not read it yet, do. Seriously. So, imagine that the electrons have some clock attached to them, and the arrow of this clock rotates very quickly, but with the same velocity for all electrons. Suppose that when the electron goes out of the electron gun, this parameter, described here as a clock, it shows 12 o'clock. And while the electron travels, the arrow rotates very quickly. And imagine that for this upper electron, it shows 1 o'clock at the arrival, while for the lower electron, its clock shows 7 o'clock. The time on their clock is different because the length of their paths are different. And for some points on this screen, the difference of the paths will be so that the clock arrows from different paths will point in the opposite directions. And in this case, physicists tell us that these two electrons are exactly in the same state, but with different signs. And since everything in these two universes, except the electron here, is completely identical, we can say that these universes are exactly in the same state, but they have different signs. Now, I promised in the beginning that there will be less formulas, but not no formulas. And here we are going to write down what we just learned in the language of quantum mechanics. This small letter A in the strange brackets will denote the state of the electron for us. The subscript 1 and 2 denotes the number of the universe. And the big letter A will stand for the state of the entire universe, except the electron, again with the subscript. Now, since the electron in the different universes is exactly the same except for the sign, we can write the whole state like this. Actually, it is how the superposition works. We can add up the states from the different universes. And if A big 1 is equal to A big 2, then you probably see that mathematically this sum equals to 0. And what does this 0 mean to us? Well, it means that there's no universe which corresponds to this superposition. And on the physical level, there's no universe where an electron arrives to this prohibited area. And for the points on the screen where electrons from different slits arrive with arrows close to each other, the result of this addition is not 0, and the superposition becomes meaningful. It can be observed. And the closer the arrows are, the higher the probability to observe the electron in that area. Now, why are we so interested in this addition? It is actually how we write the superposition of different states. Well, because this addition is really the kind of interaction between the different universes, and it is called interference. Remember, I told you that there is no interaction between universes. Apparently there is. And through this interaction, we can extract something from our distributed computation. If we manage to run different paths of computation in different universes and then make them to interfere, then we will be able to collect some information about the result from all these branches. So this is what quantum computing is about. First we split the paths, then we do something interesting in between, and then we make the paths to interfere to read the result. Sounds simple, right? Can we implement it? Well, theoretically, yes, we can. But in practice, there is a problem. Imagine that we are going to have this type of self-destructing interference. Again, small a is the state of an electron, while big A is the state of everything except the electron, in the two almost identical universes. And the subscript means the number of the universe. Now, to obtain zero, we really need both these conditions to be fulfilled. First, a small 1 equals to minus a small 2, while a big 1 equals to a big 2. Now imagine that some other random event occurs in the universe before the interference takes place. In this case, a big 1 wouldn't be equal to a big 2 anymore. And if the electron, a small, somehow interacts with the environment, it will also change a big 1 and a big 2 in the different ways. And again, we will not have our zero, and the interference will be destroyed. So, to have the desired interference, we must at least be able to do the following. First, make the computations very fast, because we need to eliminate the probability of other random events in the environment. Second, lower the temperatures of the nearby environment, again to decrease this probability. Cold systems evolve slower, so maybe we'll have more time before something bad for our interference happens. Third, isolate our computing system from the environment as well as we can to avoid, again, this interaction and change in the bigger A's. The isolation part is really hard. Everything in this list seems not easy, but isolation is maybe the worst. Even if you manage to isolate the quantum data itself, the qubits themselves are not yet the computations. You need to control and change their states, make them interact with each other, even observe each other. Yes, sometimes we need different qubits to observe each other without our observation of them. This is how the controlled gate NOT works, for example. And all this control stuff is usually achieved by the equipment much larger than the controlled system. And ideally, you need to isolate this equipment from the environment as well, since it is the part of the computational process. As I know, there is no great achievement in solving this problem nowadays. Anyway, this is why quantum computers are so short-living, so cold, and so well isolated, and still not implemented on the industrial scale.